Welcome to this lecture on research methodology. Today, we are going to explore two of the most critical pillars of any scientific study: experimental and sample designs. Whether you are testing a new medical treatment, evaluating a new teaching method, or surveying a massive university population, understanding these foundational concepts is absolutely essential for conducting valid, reliable, and impactful research. Let us start with a simple, everyday analogy to build our intuition. Imagine you are cooking a massive pot of soup for a large family gathering. To check if the soup has enough salt, you do not need to drink the entire pot. Instead, you just take a single spoonful, taste it, and make a confident judgment. If you have stirred the pot well, that tiny sample gives you all the information you need. This everyday action perfectly captures the essence of sample design in research. Now that we understand the intuition behind tasting the soup, let us look at the formal academic definition. In research methodology, a sample design is a definite mathematical plan created before any data is actually collected. It tells us exactly how to select a specific subset, called a sample, from a much larger group, known as the population. A good sample design actively minimizes bias and statistical errors, ensuring that the small subset we choose is truly representative of the entire population we want to study. You might wonder, why do we need sample designs instead of just studying absolutely everyone in the population? The primary reasons come down to time, cost, and practical feasibility. Conducting a full census is often financially impossible and incredibly time-consuming for large groups. Furthermore, in some industrial cases, like testing the maximum lifespan of light bulbs, testing every single item destroys the product. In these scenarios, sampling is not just a convenient shortcut, it is absolutely mandatory to make the research possible. This brings us to an important practical question. Exactly how many people or items do we need in our sample? We cannot just guess. We use Cochrane's formula to calculate this mathematically. Let us look at the symbols. Here, N is the required sample size we want to find. Z is the Z-score, representing your desired confidence level. The letter P is the estimated proportion of the population that has the attribute in question. Finally, E represents the margin of error. If you demand higher precision and decrease the margin of error, your required sample size will increase significantly. Before we move on, let us see this formula in action with a concrete example. Suppose you are a researcher wanting to know the percentage of students at a massive university who support a new library policy. You want to be 95% confident in your results, which corresponds to a standard Z-score of 1.96. You also want a strict margin of error of 5%, so E is 0.05. Assuming maximum variability to be safe, we set P to 0.5. Let us find out exactly how many students we need to survey. Now that we have identified all our given values, we substitute them directly into Cochrane's formula. In the numerator, we square our confidence level of 1.96, which gives us 3.8416. Then we multiply it by our estimated population variance, which is 0.5 times 1 minus 0.5, giving 0.25. Multiplying these together gives a total numerator of 0.9604. Squaring the Z-score is a crucial mathematical step because it ensures that negative statistical fluctuations do not cancel out positive ones, keeping our estimates safe. Let us move to the denominator and finish the calculation. Squaring our 0.05 margin of error gives a very small decimal, 0.0025. Notice how demanding a small margin of error creates a tiny denominator, which drives the total resulting number up. Finally, we divide the numerator by the denominator, giving exactly 384.16. Since we cannot survey a fraction of a student, we always round up. Therefore, our final required sample size is 385 students. This proves the incredible efficiency of a well-calculated sample design. Now that we know how to select our subjects using sample design, let us shift our focus to how we actually test them. Imagine you buy a new type of plant fertilizer that claims to double tomato growth. If you use it on one plant and it grows tall, can you definitively prove the fertilizer caused it? Maybe that specific plant just got more sunlight or had better soil. To truly prove it works, you need two identical plants in the exact same conditions, giving fertilizer to only one. This is the heart of experimental design. Building on that fertilizer analogy, experimental design is the conceptual blueprint within which a scientific experiment is conducted. It involves the deliberate manipulation of one variable, known as the independent variable, to observe and measure its direct effect on another variable, known as the dependent variable. Crucially, a robust experimental design must control for extraneous variables. These are outside factors, like sunlight or soil quality, that could accidentally influence the outcome. By controlling these, we ensure any changes are strictly caused by our manipulation. Why is this strict level of control so incredibly important in research? The primary power of experimental design is its unique ability to establish definitive cause and effect relationships. While other research methods, like surveys or observational studies, can only show that two things are related through correlation, rigorous experiments can prove that one thing actually causes another. It is the absolute gold standard of scientific proof, essential for everything from proving a new medical drug cures a disease to verifying a new engineering material is stronger. To represent these experimental outcomes mathematically, we use a statistical model. This specific equation is the linear model for a completely randomized design. It breaks down every single data point we collect into three distinct components. Y represents the actual observed measurement for a subject. Mu is the overall population mean, or the baseline average. Tau represents the specific treatment effect caused by our independent variable, like the fertilizer. Finally, epsilon represents random error, accounting for natural, uncontrollable variations between individual subjects in the real world. If the treatment effect is large compared to this random error, we can confidently conclude our experiment was successful. Let us apply this linear model to a real-world scenario to see how it works. A university professor wants to know if a new interactive teaching method improves student test scores compared to traditional lectures. The historical baseline average for the class is 75 points. The new interactive method is known to add a positive treatment effect of 8 points. However, a student named Sarah had a slight headache on test day, causing a random error of -3 points. Let us calculate her final observed score. We substitute our known values directly into the linear model to find the final score. The baseline mean is set to 75. We add the specific treatment effect of +8 from the new teaching method. Then we add the random error of -3 caused by the headache. Combining the baseline and treatment gives an expected score of 83. But subtracting the 3 points of random error gives a final observed score of 80 points. This clearly shows how real-world measurements are always a combination of baseline averages, treatment effects, and random noise. To visualize how we isolate these treatment effects, let us look at this detailed flowchart. On the left, we start with a large population that undergoes random assignment into 2 distinct paths. The top path is the experimental group, which receives the specific treatment we are testing. The bottom path is the control group, which receives no treatment at all. Both groups are then measured, and their results are compared at the end. This exact structure is what allows researchers to confidently find cause and effect while filtering out random noise. To wrap up our lecture, remember that experimental and sample designs are the twin pillars of empirical research methodology. Sample design tells you exactly who or what to study, allowing you to get a representative picture of the world without wasting valuable resources. Experimental design tells you how to structure your tests so you can confidently prove cause and effect rather than just coincidence. Together, they ensure that your research is both practically feasible to conduct and scientifically valid to trust. Thank you for watching.